Hey everyone. In this video we're going to talk about control loop troubleshooting. The content of this lecture comes from Chapter 6 of Chemical and Bioprocess Control, the 4th edition by James Riggs. The objectives of this chapter are we want to come up with an effective strategy for troubleshooting a feedback control loop. In order to do this, we need to understand what are the primary failure modes that can occur within these control loops and be able to determine whether or not each of the individual components are acting properly. So I'm going to start by saying that lecturing on this topic of troubleshooting is not terribly interesting. So I'm going to try to keep this video very short. And as a supplement to this lecture, what I'm really going to ask you to do is at least skim through Chapter 10 of the textbook and focus on the plots and highlight the important aspects of troubleshooting, because a lot of these things are going to show up on the quiz or exam. You can also go to the end of the chapter and read the key summary points, as those will be important. All right, so here's a control diagram of a typical control loop. So in a typical control loop, we have what's most important is our overall process. So here's our process. And again, this is just a thermal mixer. So this thermal mixer, we have the feed of a stream at one temperature. This is being controlled by a control valve. We have another stream that's being fed at a different temperature. These are mixed within the process. And we have a temperature coming out, which is what we care about, the control variable. So we're going to measure this. We're going to measure the temperature. It's going to go to a controller. The controller is going to have a specified value for which we want the system to operate, and the controller is going to tell the control valve to open or close in order to keep us where we want it to be. Okay, so in this process actually it involves many more components other than what's shown here. For example, on this slide, we can see that for a typical control loop, we're going to have a variety of different components. So let's start by looking at the actuator system. So the actuator system is typically going to be a control valve or some sort of final control element. And so this is going to be what the controller tells to change in order to keep the process at its target set point. In this case, we have a control valve. So the components of the actuator system are going to be the valve itself. Right? So this valve has a variety of components associated with it. There's going to be a valve plug that moves within a valve stem. This can get clogged. There's going to be a spring. In order to move the valve, if it's a pneumatic valve, oftentimes there's going to be air pressure. So we're going to have air that goes to the valve. So a 3 to 15 psi signal will be sent to the valve to cause it to open or close. So this IP converter is going to be a component that converts a current into an air pressure. This is going to accept instrument air, or it's the supply air. So the supply air could have potentially a problem in this process. Okay, so the actuator system essentially takes air, sends it to the actuator, the valve opens or closes. Okay, another component, we'll go over and move to the sensor. So the sensor system is shown here. So again, a sensor, it consists of a variety of things. So in this case, we have the actual sensor, which is a thermocouple that's inside a thermal well. So in this case, we have an actual sensor that's located in a thermal well inside the pipe. So the thermocouple is going to send a millivolt signal to a transmitter, which converts it to a milliamp signal, and that's what's sent to the controller. As part of the sensor, there's a variety of components, from just the basic sensor, which is a thermocouple. There's a transmitter, which is going to convert the signal of the thermocouple. The thermocouple exists in a thermal well. This is it's going to exist as a plug in a pipe. So all of these different components can contribute to the performance of the control loop. Okay, we have the overall process, and again, the overall process, it is what it is. There can be errors with the process, but those might have to be evaluated outside of the actual control loop itself, and those are going to affect the overall process performance. And then finally, we have our controller system. And so our controller system is going to consist of a variety of things. So we have operator consoles, we have the distributed control system, the DCS control computer. So here's where we'll have our PID controller. We can also have digital to analog converters, analog to digital converters. All of these different components need to function properly in order for the whole feedback control loop to work. Okay, so if you look in the textbook, we've covered all of these in chapter 2, these components, so you can revisit these. One of the important things to note, if you go back to chapter 2 at the end of the chapter, there's a table that will tell you common performance metrics for different components. It's important to at least have that chart handy, or at least have an understanding of what the specifications are for your components, so that when you evaluate the performance of your components, you can determine whether or not they're operating within the specs. And if they're not, perhaps you might need to replace the components or fix them so that they're working as they should. Okay, so troubleshooting is what you do when you know when you suspect your system of not working properly. So again, in order to suspect it of not working properly, you have to know when it's working properly. In order to know when it's working properly, it's important to document. So the main thing is one of the things, very important things for troubleshooting, is we want to have good documentation. And good documentation of our working process. So when the process is working well, you want to have data, or it's helpful to have data that shows how the process is actually working when it's working well. Therefore, by knowing when it's working well, you can determine what poor performance of the system might be. The system might exhibit erratic behavior, so you might see more fluctuations than you would otherwise expect, or more fluctuations in your control variable. Or another thing is just, one of the operators comes to you and just says, hey, our system's messed up, we got to fix it. And they might be operating with open loop or manual process control because they're not sure what to do with the overall process. So the basic steps of troubleshooting are shown here. So the first thing is, after suspecting that it's not working properly, is we need to first identify the source of the problem. So identify and also isolate the source of the problem. The next thing, so I should point out here, in order to do this effectively, in order to isolate, you need to understand what are potential problems. So again, some of this is going to come with experience, and some of it can come from just reading the textbook or looking in tables and seeing what are common problems of various components of feedback control loops. Okay, so after we identify the problem, the next thing we can do is correct the problem. So for example, if your sensor is not calibrated, it might need to be recalibrated. If there's too much filtering, you can change filtering. If a line is clogged, you can blow it out with air, etc. So correct the problem, get your system running back. The next step is you might need to retune the controller. So once everything's working again, you can retune the controller. Ideally, when you retune the controller will have similar settings to what the process was when it was working properly. Now granted, there can be a variety of other things that change throughout your process. Maybe the flow rates come in, temperatures are different, and these will require different controller settings. But again, keeping a good documentation of what's going on with your process is going to save you a lot of time when it comes to troubleshooting. Document changes. This is going to be the main thing. We want to keep a good record of how things are operating when they're operating well, problems that exist. So therefore, when something occurs later, if you've documented these problems, you can troubleshoot your process a little bit quicker. And then you want to follow up and monitor the process. Just make sure everything's working properly. Okay, so a good general overall approach to troubleshooting control loops is discussed here. So after we do things like, we can ask the operators to describe the problems or the symptoms, right? Again, you need to understand what are potential problems to know what the symptoms might actually represent. It's like, a doctor knows symptoms come from specific underlying problems, and we don't want to just mask the symptoms. We want to solve the underlying problems so that things are working as they could. Also important is to find out what's been changed lately. So there might be something that was changed to a previous part of the process that's just causing your system to respond a little bit differently. And if this is the only issue, if, for example, your temperature coming in is a little bit higher, flow rates are higher, things are now operating at different conditions, it may be possible to just retune the controller. That said, I want to point out that oftentimes, if your process is behaving poorly, one thing that people often do is they just go right to the controller and retune it. Oftentimes that can get your system working a lot better, but it can also, if there's an underlying problem, you can retune the controller and actually mask a problem that's going to limit your overall performance. Okay, so now when we troubleshoot, we want to check the subsystems separately. So like we said, we want to look at the actuator, common problems associated with the actuator. We can look at the controller, have the values change. We can look at the sensor, and then we'll look at the overall process. After we look at all of these things, we can put the entire process back together and evaluate the performance of the entire control loop. So we'll first check the actuator. And so for a flow control loop, and again, how you check the actuator is going to vary depending on the actuator. So in this example, we're going to discuss troubleshooting a flow control actuator. So for a flow control loop, we can evaluate the performance of a control valve that's controlling the flow by applying what's called a blocked sine wave. So a blocked sine wave is the main test that's used to evaluate the performance of a flow controller. So the way you perform a blocked sine wave test is you adjust the set point up and down. So if you adjust the set point up and then down by a very small amount, wait for the system to respond, okay, continue forward, adjust the set point again by a little bit more. So again, instead of adjusting the set point by a small amount, increase how much you're adjusting it up and down. So progressively increase how much you're stepping up and down in your set point, and that's going to create a blocked sine wave in your input to the process. By using a progressively increased step changes to your set point, you can see at which point does the valve actuator actually respond to the changes. Because again, valves are going to have a deadband, time constant associated with them, so we can determine those by doing this type of block sine wave. If we're not looking at a flow control loop, if we're looking at another type of loop, you can do the same sort of thing. You can apply a block sine wave to the actuator system, but in that case you might have to just open the loop, and when you open the loop you can manipulate the controller output to apply the block sine wave. We'll show what this looks like on the next slide. Okay, so once we perform this test, which we'll go into detail in a minute, we can determine what the deadband is. So how significant does the requested change need to be in order for the valve to change? And we can also estimate the time constant. If our time constant is less than 2 seconds and the deadband is less than 0.5, then that should tell us the actuator is working fine. Okay, so here's a block sine wave test. So this is what we said. So here is where we performed our block sine wave. So here's our block sine wave. Okay, so we started at the initial set point to the flow controller, and what we did is we first started with small steps up and down. Okay, if we apply a small enough step up and down, we don't expect our process to really change very much because all valves have a deadband, and for small requested changes, we don't expect the system. We expect that to really either stay within the noise or not change very much. As we continue to increase, now let's do larger steps up and down in the set point of the controller. At some point when the step is large enough, we'll see the system respond a little bit outside of the noise. By determining what's the difference between this step height, between when there was no response and a response to the system, we can determine what the deadband is for the valve process. By again, now if we do larger steps, increase the steps up and down, okay, we expect again a larger change to the process. And then we can use, in this case, when we use the larger steps, we can look at the time that it takes for the system to respond. And by looking at the input versus output, we can fit a potentially first order plus dead time model, first order plus dead time. And from this, we can estimate what the lag or the tau p is for the process, see if this falls within the characteristics of our actual of our flow control or of the control valve. All right, so this said the time constant should be about 2 seconds and the deadband should be about 0.5%. And so we can determine those things from the block sine wave test. Okay, so table 10.1, this shows a couple other common problems associated with the final control. Some of those can be excessive deadband, so maybe there's a little bit of sticking that occurs. You could have an improperly sized control valve. So if your control valve is not sized correctly, when you ask for changes when the valve's wide open, it's not going to give you very much change. Whereas you might get very aggressive changes or very large changes when the valve is nearly closed. So if you have the improperly sized control valve, you're not going to be able to achieve the control performance that you want. The valve positioner might be improperly tuned, so you may have to change this by looking at the valve positioner that's on the actual control valve, or you might have resistance to the movement of the valve stem, and this is essentially friction that occurs in your actual valve. Perhaps maybe there's something that is accumulated, there's gunk that's formed in the valve and it needs to be cleaned. Okay, so we just talked about these. These are common problems associated with the control valve. Again, looking at the table, you can figure out what are some other problems that might exist as well. Okay, so the next thing we want to do after checking the actuator, we can check the controller. So in the controller, we can ask ourselves a few questions. So are the proper modes being used for the application? So again, if we have an integrating process or we don't care about offset, we could have a P-only controller. If we have a fast process, we could have a PI controller. Or if we have a slow responding process, we could use PID. If you tuned your controller and you documented your process, you should have a good idea for what your values are of Kc, tau I, and tau D. Now I suppose there's a chance that these values may have changed, so someone may have gone into the controller and changed these values. Ideally, if they did that, they would let you know. But there's a chance these values would have changed, and that's what's causing the performance to change. So again, you can look at maybe the derivative term was added and it doesn't need to be there, or there could be other things associated with the mode of operation of your PID controller. So that's something that's good to check, but of course you have to have documentation so you can compare that to previous settings. Next thing is the controller tuned properly. Again, you can look at the tuning of the controller based on previous settings, or you can just apply some very small changes to your process to see how your feedback control process responds. Perhaps retune the controller as is. But again, the problem here is that if you can retune the controller, and you can end up masking some underlying problems. So it's important to go and look at what are some of the other symptoms that are showing up because of what's occurring in your system, and how are these changed from when the system was fresh and running well. All right, next we can check the sensor system. So the sensor is going to be, what's making the measurement. So sensors can be problematic. They have noise, it has to be filtered. You could have too much filtering. The sensor could be out of calibration. It could be, lines to the sensor could be clogged. There's a variety of things that can happen with respect to the sensor. So some of the things that we want to do for the sensor is we want to evaluate the repeatability of the sensor when there is no changes occurring to the process. We can look at sensor dynamics, so we can cause a known change in the process. It might require an independent measurement of the control variable using another type of sensor system. But again, these are types of things that we can do. We can calibrate the sensor by having another independent measurement being made. To see more specific possibilities for different sensors, you can look at table 10.2 in the next couple slides. So again, there's a variety of things that can happen with a sensor, and this is really going to depend on what type of sensor that you have. Ideally, you'll have the specifications, instruction manual, other components of the sensor that can help you troubleshoot the sensor and figure out if the sensor is working properly. Like we said initially, does the filtered signal to the controller represent the control variable adequately? Like we saw in a previous lecture, the sensors are inherently noisy, and often the sensors will have a filter factor to filter out the signal, and this can affect the performance of the feedback control loop. Again, if someone changes the filtering, ideally they would have let you know, but maybe that's not always the case. So having a known measure of the filtering is important when going into this process. Okay, so here is a general sensor troubleshooting checklist. All sensors are going to have some sort of transmitter, so a signal is going to be sent from the sensor, so what's actually being measured, to the controller. For example, in a thermocouple, you might measure the millivolts, so that it specifically measures a millivolt and then converts that to a milliamp signal, and that signal is filtered and goes to the controller. For temperature sensors, the important things that we need to think about are calibration, location, and cleanliness of either the sensor probe or maybe the thermal well in which it is in. So sensor probes and thermal wells can foul, so stuff can accumulate on the surface. When you have fouling that occurs within the sensor, this is going to cause a lag or a delay in the sensor response. So we can compare the lag associated with the sensor at some random time with a time when the sensor was just recently installed and you expect it to be fresh and clean. We can look at pressure sensors. So oftentimes pressure sensors can have problems associated with plug lines. So if the line going to a pressure sensor becomes clogged, you're not going to be able to get a good measure of the actual pressure, or it won't change in the way that you would expect it to. This is a good time for me to pause, because one of the things that you'll need to do is when we discuss later in quizzes or on exams some potential problems that occur, you'll need to determine, you'll need to correlate the symptoms with an actual problem. So, for example, if you're measuring a higher temperature than you would expect, the reason that you assume the sensor is higher should cause the sensor to be higher temperature. If you're saying that the pressure is lower than the pressure that you expect, the symptom that you're attributing that lower pressure to, it should physically cause the system to be a lower pressure then. So it's really important to think about what the problem is and how it affects the symptom, and make sure that your problem and your symptom are moving in the same direction. Okay, sampling systems for GCs and other analyzers could have plug lines. Flow indicators, again, flow indicators, level indicators. Many of these types of different sensors have lines that go from the process to a sensor measurement, and if these lines are clogged, they can cause the system to respond in a specific way, and also negatively affect the process. Here's table 10.2 from the textbook. I would advise you to just read through this, make some notes. This is going to tell you some of the common problems associated with a variety of different sensor components and sensor types. So for example, you have thermocouples or RTDs, you have pressure indicators, so these can have plugged lines. You can have condensation that occurs in the pressure indicator. You can have confusion about absolute pressure versus gauge pressure. Let's see, flow indicators, a variety of problems. You can have plugged lines, you can have damage to the orifice plate, something is installed incorrectly, and then level indicators, again, plugged lines, something on the level indicator itself is actually broken, or in all of these cases, your sensor itself might just fail, so it might not be able to work as properly as it should, no matter what you do. So in that case, it might need to be replaced. Okay, so finally, a couple other factors that affect the performance of a control loop are going to be the type and magnitude of this disturbance. So maybe your system is just not behaving now because the type and magnitude of the disturbance has changed, and this is going to affect the variability of your CV. Again, the important thing to note this, documentation. Document what are the type of disturbances you expect. Make a note of how fast these are removed by your system. Perhaps there's some nonlinearity that's occurring. Your controller is very good at getting rid of small disturbances. Now all of a sudden you have a large disturbance that causes your system to become unstable, or just have more variability than you want to have in your process. There's a lag associated with individual components, so your actuator, process, and sensor. So when we combine all these things together, you have disturbance, slower disturbance rejection, which affects variability. Once all of the individual loops have been tested and everything's put back together, we can go ahead and look at our overall process. And again, we can conduct what's called a closed loop block sine wave test. So this closed loop test is done by performing set point changes. Previously, when we looked at flow loops, we were doing a closed loop block sine wave test, but this could be something that could be done on the overall process. So for the example with the thermal mixer, so the thermal mixer that we showed in the initial few slides, the control variable is going to be the temperature coming out. The set point is going to be T specified. So in closed loop, we're going to perform small steps, and then we're going to slowly increase the step and see how, at what point we see the process respond, and then also does the process respond as it should, what's the time constant of the process. And really the important thing here is that we can compare these later block sine wave tests to the initial, to the documentation that we have when our system was working properly. So again, it's a good idea to, to save yourself some time and effort is you can run this when all is good. If we run the process when all is good, we can get a good indication of what's going on when we notice problems occurring in our process. Okay, so the closed loop deadband, it gives an indication of the effect of the actuator deadband and the sensor noise, along with the resolution of the analog to digital converters. The closed loop settling time is going to be indicative of the combined labs of all of the loop components. Again, these are things that you can determine and calculate theoretically as well. You can also determine if your controller tuning is done properly. And then if possible, we can observe disturbance rejection to determine if the major problems have been corrected. So these are what you want to do when the system is working well. Perform this type of test after your system has been corrected and make sure everything is working as it should. So again, just to kind of show some potential problems with the controller might not be tuned well. You might have too much filtering on the measured CV. That could be a sensor problem. Your analog to digital converters could be problematic. You might have improper selection of your direct acting or reverse acting on your controller. We looked at that in Chapter 7. It's important that your controller is operating with the right mode. Okay, so as an overview, to summarize, we want to keep our control loop running properly, so we need to understand the processes that's being controlled. We need to understand what are the possible failure mechanisms in the process, and we have to have enough knowledge of the process that we can go from the symptoms to identify the problems, have the know-how to correct the problem, retune the controller, and get everything back online. Okay, so that's all I want to talk about today for troubleshooting. This was, short with the main points presented. As a supplement to this video, I'm going to ask you to go read through the textbook and make sure you focus on anything, especially those things that we talked about here, and just look into that in a little more detail. Read to the end of the chapter summary. So that's it for today, and we'll see you next time.